save, open new file, paste the program, save the program. So sqr where I am, so I am in internal DAC, sorry. Let me go back to the folder which I created just now. So it was external DAC, external DAC square. Here I'll give it as sqr.c. the program is saved. Add it to the source group, square.c. so program is added. Do the option settings for the target one, go to output, check X file, linker, use memory layout from target dialog. Okay, now compile, 0 errors and 0 warnings, build. Yeah, so now this cannot be simulated here. Now even if I go to debug, so I cannot debug, simulate here, because this is not an internal DAC, this is an external DAC. And logic analyzer, if I go, it will not happen. Setup, create some variable, new variable, a out, close, and say run. Nothing will happen, nothing you're getting. That means this is not from the internal DAC, so this is from the external DAC. Let me stop debugging, because this way I cannot simulate. Now I have to go to the protest simulator. So I have already made one, created. So just go back. So external DAC, this is the one. The entire circuit I've already designed. I'll just show you now. So this is what the external DAC is. This is the external. This is the same connection which you are seeing from the first lab program of part B. So this is what the DAC 0808 which we are using. So analog pin, 8 digital inputs, A1 to A8, from where they are given. See here, P0.16, P0.16 to P0.23, P0.16 to P0.3 connected in that order. 0.16 is going to A1, 0.17 is going to A2, connected here, and minus VDC to VEE, and then V reference with a resistor to the ground, and plus V reference to plus 5 VDC, and this is an operational amplifier which is used, LF351, because to amplify the signals and to get the better clarity of the output waveform. And this is from the output pin 6, we have the connected to one channel of the oscilloscope, digital oscilloscope, here to A, and even earlier I showed you can connect it to any one of them. Now this is how the connections are made. You can just go through it in the video, and you can try to make the connection similarly. You know the components, you can just go here and search for those components here using those keywords. You'll get those components, add them here, and then use it and try to build. Okay, and this is the oscilloscope. I have told you where to get this oscilloscope. Here you have to go, and then this oscilloscope, you can use it. And one more thing, here I have shown you the voltmeter also. How to get the voltmeter? Again here, probe pins, probes. This is voltage meter. You can place here. I have placed here, and the rest all I think you are familiar. This is the power source, and this is the resistor, this is the op amp. Its number is written LF351, and this also, and the rest all ground and capacitors. You can use it. Now let me write the program to this. My X file, my X file is in the folder external DAC square, and this is square sqr.x. open. Okay, now I'll just say simulate. Now when I say simulate, the digital oscilloscope will open. Yeah, it's giving. Only thing is I've given the more time range. Let me reduce it. Yeah. Yeah, it's coming. Let me move it little upper and reduce the amplitude also, so that you'll have a better look. Yeah, there's a square wave which is being generated, the square wave. And these are the other, this is channel B, this is channel C, and this is channel D. If you don't other channels, if you don't want them, you can just put them into off. So just pull this down. See, this is gone, and channel B gone, and then channel D also gone. So this is what the digital oscilloscope, and this is the simulation, and the you can see the voltage here. See, it's changing from 0 to 3.35, 0 to 3.5, 0 to 3.5. So what we are giving the digital data from 0, 0, 0, 0, 8 zeros to 8 ones, 8 ones. Now it's getting converted to voltage 0 and voltage 3.5. So this is what is the analog data, giving the digital data, converting it into analog, and this is what this waveform says, it is analog. Now similarly, let me stop this. And you can just see the data which is going here also when I say simulate. Yeah, this is a waveform you're getting. Let me drag this little the side. You can see your data. We're supplying zeros, ones. Now when you get all blue, it is 0. When you get all red, it is ones. And the same thing is coming here. Same thing is coming here. And that leads you to this waveform. Okay. Now let me stop, and we will go to the next program, that is triangular wave, a program using external DAC. So this is triangular wave, a program using external DAC. If you have understood the square wave, then external triangular waveform using your external DAC is also easy. LPC 214 header file, same thing, and temp initially I'm initializing it to all zeros, and main I is initialized to 0. Pin cell 1, pin cell 0 I'm not using. Actually that was not necessary, pin cell 0, because all my pins 0.16 to 0.31 says 0.23 in the range 0.16 to 0.31. If you make pin cell 1 is equal to 0, that is enough, but this is not necessary, but we have written, nothing will happen. And here we have applied it, pin cell 1 is equal to this, and I want to make again P0.16 to P0.3 as act as output pin, IO0 DAR, same thing. Now output 0 to FE, so this is what I'm doing now because I want the waveform to go like this. Just observe my mouse movement. I want the waveform to go like this and waveform to come like this, correct? No? So this is what this loop will do. This it will make the waveform go like this, increasing, and this for loop will make the waveform decrease like this. Now phi is equal to 0, I not equal to 0 FF, I plus plus. Now assign the initial value I to temp, 0 to temp. Now 0 temp is equal to temp left shifted by 16 times. Why you got to left shift it by 16 times? Because you have to take the 0 data to the position P 0.16 to 0.23. So because this will occupy from 0.0 position, but I want this data to be exactly present at the pin number, port pin number 0.16 to 0.23. Now this is 0.16. How many left shift I got to do that in order to take it to the 0.16 position? 16 left shift we got to do. In the internal DAC, we were left shifting it by 6 bits because it was starting at 6th bit till 15th bit. 6th left shift was you were doing. Now here, since the port pin which you are using is P0.16, now I want the data to get positioned from P0.16 to 0.23. 16 left shift you are doing, and then assigning it to IO0 pin. The moment it is assigned to IO0 pin, so it goes to the DAC, and from there it gets converted into analog data, and then it is displayed. And similarly the other for loop, from FF to 1. Now you cannot go to F0 to FF, FF until FF, because one step minus I'm doing 0 to FE, because it is an 8-bit DAC and it cannot accommodate even one more than this FF. Now 0 to FE we are going, and in the reverse order we are coming to FF. From FF we are going it till 0. So again FF is assigned. So down count FF is assigned. It starts from the peak point, and then left shift it by 16 times, and then assign it to pen, and every time this loop is called, I is decremented so that you get the other loop. So other part of the waveform, triangular waveform, that is decreasing one. Now this is the program. Yeah, and that's it. Now let me execute this program quickly. So I'll copy this. I'll not create one more project. Let me use the same thing. I'll replace this program. Yeah, this is the triangular wave program. The name of the program is sqr.c. Don't worry about this. But the program is a triangular waveform program. Let me compile it. So build the X file. Yeah, done. Now I'll go to this simulator. Okay, open this, open the program. Now name of the file is square.x itself, because the same name I'm using, but the program is triangular waveform program. Now I'll just say run the simulation. So run the simulation. Yeah, some fine adjustments to get the waveforms. I think I have to do the adjustments here. One second, I'll show you. Yeah, it's there, but not coming properly, and so I think I have to increase. Yeah, it's something like a triangular waveform, increasing and decreasing, increasing and decreasing. And you can observe here also, in the previous experiment the output voltage, it was jumping from 0 to 3.5 volt and 5.3 to 0, but now it is increasing. You can see here it starts from 0. You observe there, it starts from 0, 1, 2, 3, it goes like that, and it is coming down. Now this is the waveform, and I tried this, and to some extent it is okay, but I think some fine tuning is required for this adjustment. If I do that, I'll get the triangular waveform, exact triangular waveform. I think I have to bring it little down. The triangular waveform, the frequency is more. Okay, now with this I'll stop here. With this you people understood how to interface an external DAC to LPC2148 and generate the square and triangular waveform, and you also understood how to use the internal DAC which is there inside LPC2148 and generate the square and triangular waveforms. Thank you. In the next class, till now I've completed 4 programs from part B, and there are remaining 4 programs. So I'll try to complete those programs soon. Meanwhile, I'll be continuing with the module 4. So thank you.